Hello, everyone. Greetings from Austria to Australia. I will present you the work that I'm doing with my colleague Stefan Uttenthaler at the University of Vienna about infrared luminosity, period luminosity relations of galactic Miras based on multi-epoch photometry and what they can tell us about the Gaia Parallax precision. So I guess that most of you know that long period variables follow period luminosity relations. The longer the period, the higher the luminosity. And these diagrams are a powerful tool for understanding stellar evolution. And we learned a lot from them, from studying these relations, in particular in the Magellanic Clouds. There are many stars at the same distance available, and there are also many surveys of the Magellanic Clouds. Only show one example of many here, which is a figure from the work of Igor Sostinski and Peter Wood. And I'm going to focus on sequence C here, which is this one, which is the Mira sequence. There are also still some challenges in these period luminosity diagrams. For example, the nature of the sequence D stars is still not fully clear. In any case, if we look at the period luminosity relations in the Magellanic Clouds, we see that they are very well defined, mainly because these stars are all at the same distance. And there are also surveys, multi-epoch surveys available that where we can add several observations to average out the variability of the stars. So, however, if we turn to the Milky Way galaxy, we face a problem with the distances because they are poorly known for galactic AGB stars. So Gaia parallaxes are to some degree uncertain because of the large extension of these stars and the effect of the surface brightness variation, which is caused by the atmospheric dynamics of these stars, which has been shown by AAVSO and collaborators in several works. So there are, as a result, there are only few literature works on period luminosity relations of galactic AGB stars, of galactic Miras. And with galactic, I mean the solar neighborhood, basically. So the literature is much more sparse on this topic. I'll show you one example from Patricia Whitelock and collaborators. They used parallaxes from Hipparcos, which are the circles here, a very long baseline interferometry parallaxes, triangles, and also some globular cluster stars here, which are the cyan symbols. Recently, there was a paper by Andrei Antsara-Laza and collaborators. They used parallaxes measured from the VLBI on maser spots to, as they say, calibrate the Gaia parallaxes. And for the construction of the period luminosity diagram, which I show here, they used only the VLBI parallaxes. And they had to exclude some of the outliers here. So one is left with very few stars to construct a period luminosity relation of galactic stars if one does not use Gaia parallaxes. The second problem is that AGB stars are strongly variable, but unfortunately many surveys are only single epoch, and this is also true for the 2-mass survey, which is often used, and this single epoch introduces additional scatter on the period luminosity relations. So one example that uses 2-mass is shown here. This is a diagram from the paper by Thomas Lipzelt and collaborators from last year. This is a period luminosity diagram of solar neighborhood long period variables based on Gaia parallaxes and also Gaia periods, and the 2 mass KS single epoch photometry. And you can see here this is the Mira sequence. One can see it, but it's still not very well defined, also because of the single epoch 2 mass data. Alternatively, one can use a large sample, like is done by Sanders. He made a probabilistic model to derive the period luminosity relation of galactic Miras. So this is also 2 mass magnitudes here and Gaia parallaxes. The density plot here in the background that uses all Gaia parallaxes that are better than signal to noise 1. And if you make a selection of a parallax precision better to 10%, you get these dots here. But as you can see, there are still large outliers on this diagram. So there's a solution. There's this panel, I have to exclude it. There's a solution to the second problem, namely we can turn to multi-epoch infrared catalogs that are available and which we did for the present work. One of these catalogs that we adopt is from Price and collaborators from 2010. It's a 3.6 years observations of DIRBE near-infrared stellar light curves in 4 infrared bands. The DIRBE instrument was mounted on the COBE Cosmic Background Microwave Explorer observatory, and it observed the sky in 4 infrared bands basically between the J band and the M band. And the second catalog is from Meissner and collaborators from last year. It has the interesting name Untimely. It's a full sky time domain catalog based on WISE observations from the WISE infrared satellite. And it contains, on average, 16 observations in the WISE 1 and WISE 2 bands spread over 10.5 years. And this is the wavelengths of these bands is at 3.4 and 4.6 micrometer. So 16 observations is already way better than the single epoch 2 mass catalog. I show examples of light curves from these catalogs. This one is in the DIRBE 2.2, so basically K-band data. So these are examples of one star with a full amplitude of 1 magnitude and a second one with 2 magnitudes in the K-band. So you can see that these stars are still strongly variable even in the infrared. And if you pick only one single epoch from those observations, then you will end up with some additional scatter in the period luminosity diagram. I also have light curves from the WISE observations, and this is the Mira Helix Cygni in the W1 and W2 bands. And also here you see that the star varies by more than a magnitude in W1. And we combined these data with pulsation periods taken from optical Mira light curves that are collected by a Swedish amateur astronomer, Thomas Karlsson. You find them on this page here. And he also makes plots of the period evolution of these stars. This is that's a collection of 510 optical Miras. The example that I'm showing here is famous Mira itself. And as you see, it slightly varies its pulsation period over time. And if you want to have the pulsation period exactly taken at the same time, observed at the same time as the infrared observations, you can go into the table and pick exactly the period that the star had when it was observed in the infrared. And you see that the periods are not fully constant too. So further input that we know used for the work is the first one was the variable star candidates from the Price work from table 1. We cross-matched this with the stars from Thomas Carlson to obtain the pulsation period. We used Gaia distances from Baylor Jones and collaborators. We also did an extinction correction, as you can see. And we combined the parallax and photometric uncertainty to find an overall uncertainty on the absolute magnitude. And we define a gold sample with parallax precisions better than 10%. And we end up with a sample of 109 Miras, of which 91 are pure M stars, 8 are S or MS type, and 10 are carbon stars. So there are too few carbon stars to make a fit for them separately. But in general, we have quite a substantial sample. And if we plot them, for example, in the DIRBE 2.2 micron band, we get a diagram like this. So there is this gold sample forms a relatively tight sequence in the period-luminosity plane. There are no strong outliers. Well, there's one star that we excluded from here, Alpha and ACES. It was a strong outlier, but we saw in the AAVSO light curve that during the time of DIRBE observations, it went through a marked minimum, and we excluded this one single star. And the scatter around this period-luminosity relation is slightly less than 0.3 magnitudes. If we plot the same using the 2-mass K-band magnitudes, the scatter increases markedly. It's at 0.38 magnitudes roughly. It does not seem much, but actually you need to add a 0.2 magnitude additional scatter in quadrature to go from this scatter of the DIRBE magnitudes to the 2-mass magnitude scatter. So the DIRBE observations considerably reduced the scatter around this relation. We did the same for the untimely stars. We downloaded all the WISE observations with the untimely catalog explorer and combined this with the periods from the Carlson sample. And we did the same extinction correction and parallax adoption as for the DIRBE sample, and we end up here with a gold sample of more than 300 stars, also most of which are M-type stars and a few carbon stars. And this is the diagram that we get in the W1 band at 3.4 micron. Also here, it's a very well-defined relation. The scatter is slightly larger than in the DIRBE band, but not by much. Also here, there are no extreme outliers. So from this diagram, we did not exclude any single star. I'm not showing the W2 band version here because there's some problem with saturation that we still have to analyze. But the W1 seems to be without saturation problems. So, and we made linear fits to all of these data, and I collect them here in this table. Of course, you don't need to learn the numbers by heart. This is ordered by increasing wavelengths here, and you see that the absolute magnitude increases, of course, with increasing wavelengths, and also the slope changes. I want you to focus here on the DIRBE 2.2 band and the 2-mass and this the white log relation. You see that the DIRBE relation, or the absolute magnitude, is almost exactly the same as the 2-mass. and only slightly fainter than the Whitelock relation from 2008. So it's the comparison is quite favorably. And this brings me now to the second part of my talk, in which we use this period luminosity relation to estimate the Gaia parallax uncertainty. So one can use the scatter around the period luminosity relation to quantify the if the uncertainty given in the Gaia catalog is realistic or not. And for this, we made a simulation with a grid of Colibri AGB models that are from Giada Pastorelli and collaborators. We have, I think, about 10 different stellar masses. They're plotted here in this diagram with different colors. And of course, the stars move across this diagram here because of the thermal pulse cycle. And also the different masses cover different areas of the diagram. And this here is only the fundamental mode pulsation that we show of these models. So we did a bootstrapping exercise from all these model points. I can have a bonus slide with all the technical details, but maybe I can say that we selected the model stars based on a Cooper initial mass function. So the higher the mass, the less likely the stars are selected, and also it depends on the time that the model star spends in a certain time step. Here the symbol size is scaled to the probability that a model star is selected. And we can also make linear fits to these model period luminosity relations and evaluate the scatter. And if we do this for many bootstrapping samples, we get an average, and this is also slightly more than 0.3 magnitudes. So we do this in the K-band to compare to the DIRBE 2.2 band, and you see that this is almost exactly the same. We almost exactly arrive at the DIRBE scatter in this diagram. And I should also mention that we did not include any extinction uncertainty and no only solar metallicity, so no spread in metallicity, and still they are almost exactly the same. So this probably means that the Gaia parallax uncertainties cannot be much underestimated. Miura, in her work, estimated error inflation rates of the Gaia parallaxes by comparing them to VLBI parallaxes and assuming that the uncertainties of the VLBI parallaxes are correct. And they find that for the bright stars, the Gaia parallaxes must be inflated, or the uncertainties must be inflated by a factor of more than 5 to agree with the VLBI parallaxes. And we can also check this with our work with the period luminosity relations. I did this for the WISE-1 band. I split the sample at Gaia magnitude 9 and evaluate the scatter of the bright and the fainter sample. In fact, the brighter sample has a lower scatter around the linear relation than the overall scatter. And this probably means that the parallax uncertainties of the brighter stars cannot be uncertain by a large factor. So this is probably not in agreement with what Andrea and Zahra-Lazar find with the comparison to VLBI parallaxes. So the Gaia parallax uncertainties appear not to be underestimated by much. So I arrive at the end. I have 2 take-home messages. So with the multi-epoch infrared catalogs and Gaia parallaxes, we can construct well-defined period luminosity relations of galactic Miras. And the scatter around the period luminosity relations indicate that the Gaia parallax uncertainties cannot be underestimated by much. In conclusion, I would like to convey some confidence in the Gaia parallaxes of AGB stars, in particular Miras, and the uncertainties. And the data that I present indicate that they may be more reliable than sometimes reported in the literature. But I also think that more tests on parallax measurements are certainly needed. Thank you.
Hi, nice talk. I work on Miras too, and I would like to believe that they're more reliable than previously stated, but I kind of struggle with that having looked at Gaia parallaxes myself. So I have a couple questions. First of all, it's not just Adrit Salara, I'm butchering her name, that found that bright stars have underestimated uncertainties in Gaia. Like there's a paper by Karim El-Badri where he looked at 1 million binary stars and used the parallaxes of the binary companions to accurately derive parallaxes for the stars that they were struggling to get good parallaxes for. And he also found that brighter stars have underestimated parallaxes with Gaia. Secondly, I have another thing I'm curious to get your thoughts on, which is that you said that your models show that the scatter in the 2.2 micron PL relation is about 0.3 magnitudes. That seems very large, especially if you look at the K-band PL relations from like the LMC or the SMC or any other local galaxies. So I'm curious in that case why your models are producing so much more scatter than empirical data seems to.
So first, I think I don't know this first paper that you mentioned. I would be curious to.
Okay, I'll send it to you. Yeah, because this paper was
you can send it on Slack maybe.
Yeah, I will, because this paper isn't just looking at AGBs, it's like all different types of bright stars. The underestimation of their parallax errors are not just a problem that AGBs have, but with many other bright sources in Gaia as well.
So I want to make sure I should say that so it's not about the parallax itself. If it could, I mean, there's this problem with the 0 point.
Right.
So yes, there's I didn't look at the into this 0 point shift, but it's about the uncertainty. If the uncertainty of the parallax stated in the Gaia catalog, if that's reliable or not. So, and that's what seems to be the case from my investigation here. But concerning the comparison with LMC and SMC, that's a good point. Let's maybe go back to the plot here. I don't have the numbers here, how much the scatter in the
sequences. I would say this is not like an example of a clean PL relation for Miras from the LMC or SMC. Like if you look at samples where they are looking only at Miras, and you can see some of Patricia Whitelock's other work, I believe she finds much lower scatter than 0.3 magnitudes.
Okay.
Yeah,
that's a good point.
I've also looked at myself, I've looked at more distant galaxies and found significantly lower scatter than 0.3. And that's at galaxies that are not in our local group. Of course, it's not using ground-based instruments, but I guess I would expect the theoretical limit to be much smaller than 0.3 magnitudes in terms of the width of the PL relation.
So, and this is the relation of the total grid that we have, and so I mean you see that there's some scatter. Of course, all these points they are have different probability of being observed, and so this is one example here, and overall that's 0.3, that's what we find from this grid, which is solar luminosity, not luminosity, sorry, metallicity. I don't know, could it be a metallicity effect? I don't know. Maybe there are some molecular bands that affect the scatter. Also, I know that the carbon Miras, they have a larger scatter than the oxygen-rich ones.
They're all good.
This could point to some effects of molecular bands, but I don't know. It's a good point.
Yeah, I mean, I think it's interesting. I don't know what is the cause in the models either, because I haven't tried to derive the scatter using any models myself. But for example, in the LMC, I think Patricia Whitelock got like 0.13 magnitudes in scatter for oxygen-rich Miras. And I agree with you that carbon-rich Miras have larger scatter. But at 2.2 microns, I don't know if that's even that large. So I guess, yeah, I would be surprised if this really was the width of the Mira instability strip, so to speak, that's causing this. But yeah, I mean, it's very interesting. So I'd like to talk about it more if you're up for that. Yeah. Okay.
Yeah, if you could put that in Slack, that would be interesting.
Okay, sounds good.